Okay, so what we're going to do today is talk a little bit about reactivity of carbonyl functional groups. So, what kind of things do you think would be involved in determining how reactive a carbonyl group is? Think about SN2 reactions, right? If you have an SN2 reaction, these are nucleophilic reactions where a nucleophile attacks. So you have to think about where it attacks has to have what kind of charge? Positive, right? And the nucleophiles will be just what we've always talked about, right? Negative charge, lone pairs. Those would be good nucleophiles. We're going to add another criteria to all of this. Is that we can classify nucleophiles as either being able to add and not come off, so irreversible, or we could classify them as reversible. That nucleophiles like iodine, right, I minus, great nucleophile, also great leaving group. And as a result, for carbonyl functional groups, iodine usually doesn't do a reaction at carbonyl that produces a product. Okay? The other things that we have to think about is sterics. All right? So we have sterics, we're going to have charge components, right? And we're going to have bond strengths. Like how strongly does the nucleophile bond? Okay, so let's talk about charge. And really when you're talking about charge on a carbonyl functional group, C double bond O, right? You can think of a couple of different things. The oxygen has resonance contributors, and in the resonance contributors, you can put a positive charge on the carbon. This is where the nucleophile will attack. Okay? And so you have resonance. The resonance hybrid, if you were to draw it in on here, I mean, it's a kind of a silly resonance hybrid. It goes like this. It kind of just looks like the thing that's right next to it. So if you have a dashed line, right? But that creates quite a bit of positive charge at the carbon. Other things that you can think about is inductive effects in terms of their reactivity. Just because the oxygen's more electronegative, it also creates a positive charge. Okay, so those two things work together in this case to make the carbon on the carbonyl functional group very electropositive, which means what? Nucleophiles like to attack at that point. Now, if you think about SN1, SN2, that kind of stuff, right? In an SN2 reaction, the nucleophile has to come in and has to get by the groups, right? Remember you have like the gang of people behind you, and if you're really big and bulky, nobody can come and do the backside attack. Well, it turns out that criteria is not as important for the reactant in this molecule, because when a nucleophile comes in and attacks this carbonyl functional group, right, the molecule is trigonoplanar. So whereas in a SN2 style reaction, the groups are back and the angle of approach is really small, for a carbonyl, an sp2 hybridized carbon, right, that angle of attack is pretty big. It can come in instead of directly from behind. It doesn't have to come from here. It can come in from here, and then it has this whole 180 degrees of open space where it can come in from. So sterics on the attack is not a big deal. But what happens over here? Right? It's tetrahedral now, right? So this angle, if you think about the angle from here to here, like in the plane, that's 180. And if you look at these angles here, these are 120. But when you form your product, right, now it's sp3 hybridized. And so the size of the groups will matter, because now you're going from a condition of low energy where everything's far apart, and then now it's tetrahedral at the product. And that tetrahedral nature of it tends, if the leaving group is if the nucleophile is also a very good leaving group, tends to kick the nucleophile out. Okay? Part of that being, too, like a lot of the good nucleophiles are large and they're bulky, so as soon as it becomes tetrahedral, that creates strain and it spits out. Now, part of that strain depends on a couple of things. Size of the nucleophile, but the other thing that it depends on is the size of these R groups. Okay? Those groups are really big, right? The nucleophile wants to come in, can't make the tetrahedral intermediate very easily because you got to push the big groups together in order to do that. On the other hand, if those groups are really small, right, like hydrogens, then what happens? Well, when you try to push them apart, they're just hydrogens, so you just push them out of the way. They're small. Okay. What this affects ultimately is equilibrium of the reaction. If you have small groups, R groups, tends to favor the product side. Like two hydrogens tends to favor the product side. If you have one hydrogen in an alkyl group, that's less favored. If you have two alkyl groups, it's even less favored. Okay? So equilibrium position in a reaction is going to be determined in part by the size of those groups. Okay, so let's take a direct comparison. Now, this is kind of a horrible electrophile over here. Because I don't know why they decided to put two T-butyl groups on it, but we can talk ourselves around that. I should have fixed it and made it something simpler. Which one of those carbonyl carbons, okay, there's this one. Well, let me do it in a pretty green color because I can now see that color on my beautiful projector. Which one of those carbons has more positive charge? In other words, which one's a better electrophile? One on the left. Yeah, aldehyde, because it doesn't have the alkyl group, right? These alkyl groups are electron donating groups, and they tend to push electron density towards that carbon. Okay, so this one is more electrophilic because the hydrogen can't hyperconjugate and donate electron density. Plus, there's a lot less steric strain in that location. So in terms of intermediates, it's going to be a lot more receptive to picking up a nucleophile. Yeah, so this is a much better. Turns out aldehydes are always more reactive than ketones, simply because you have similar classes, like similar kind of alkyl substituents, because they're more electrophilic and there's less sterics involved in the intermediate and the transition state. So here's an example. This is what I was talking about. Let's say you have this electrophile. We say it's more reactive, and it is. Iodine is a great nucleophile. It comes in and attacks, and then you're left with this. This is your intermediate, right? So if your nucleophile is weak, right, that means, in this case, a weak base. How to say this? Sorry, let me back up. If your nucleophile is weak, it can't attack well. So the same, I was thinking, oh, that's kind of all backwards what I was about to say, backwards from like the way I've described it before, so I'm going to just change what I'm thinking. If your nucleophile is weak, so no negative charge, right, sterically hindered, right, it doesn't attack well. And also, if your leaving group is a good leaving group, once it attacks, even though it's a good nucleophile, because of the sterics involved in the intermediate, it gets spit right back out. So no reaction, okay? It may form the product quickly. It may form this very fast, but because if you're looking for this with an iodine here as the product, you won't find it, very much of it, simply because equilibrium favors it being over in this position, okay? Okay. I'm going to skip this next slide. I'll come back to this one. I did it right away last time, but I didn't like it, so I'm going to just come back to it later. So here's an example of how these reactions would work. Okay. So if the nucleophile is strong enough to attack and not a good leaving group, okay, then what happens is it attacks the carbonyl. So here's my nucleophile. You get a negative charge on the oxygen, which then you can protonate in solvent, and you end up with this as your product. Okay? You've seen this reaction before because, if, like, you remember the sodium borohydride or aluminum hydride reactions, lithium aluminum hydride reactions. This is how those reactions work. That is, if I put a boron in here. Oops, better use a pen now. Put my boron here. Hydrogen's here. There, I'm lazy. I don't even have to redraw the arrow. The hydrogen transfers over, right? Like that. You form this as your product, where the nucleophile is the hydrogen. And hydrogen is a horrible leaving group, so it doesn't leave, right? And then at the end, we usually protonate this with solvent. Oopsie, I lost connection. I figured something out about my network connection. Is if I'm standing over here, it stops working a lot, like it just did a little bit ago. And if I'm standing over here, it seems to work okay. And I think it's because the connecting point is just behind the corner of the hoods. So if you feel like I'm ignoring you over there, it's because the Wi-Fi has trained me to stand over here. It's like I want to go over there and talk, so I walk over there, and then I lose connection, and I stop recording and all that kind of stuff. Sorry. So if you want to be near me when I talk, sit over here. Okay. All right, so this is how you get your product, and this would be a hydrogen. And this, again, is the mechanism that we saw before with the carbonyl to form secondary or primary alcohols. Okay? Okay. So let's say you have a bad nucleophile, weak nucleophile, okay? Example of a weak nucleophile would be something that has a pair of electrons but no negative charge, right? Common example would be something like water, right? So let me back up for a second, and we're going to look at this list of nucleophiles. Which one of these, in this list, which of these nucleophiles is strong and which one is weak? Huh? Yeah, R minus, definitely strong nucleophile, right? Also strong base, right? Hydrogen, hydride, right? That's also strong. OH minus, definitely a strong nucleophile. And Cn minus is a good nucleophile too because it has a lone pair and a negative charge. So in this list, really, like the bad nucleophile that's really common is water, okay? So this one's weak. So let's look at what happens, how you make it possible for a weak nucleophile to attack and with efficiency, make it fast, okay? Okay, so the common trick in using water as a nucleophile and ending up with water added to the carbonyl is just to add acid. If you add acid, what happens is it protonates the oxygen. So it has to be a strong acid, right? And that makes that pair of electrons pull away even stronger. So in the resonance contributor, there's even more positive charge at the carbonyl carbon. So it becomes more electrophilic. So you don't modify the water as the nucleophile, you modify the electrophile, right, the carbonyl group, by making it more electrophilic. Okay. So when you do these nucleophilic addition reactions with water, the first step is actually to use an acid to protonate that carbonyl functional group. So the mechanism looks, something like this. Strong acid, right? You attack the acid, you protonate this, and then the nucleophile, which could be water, would attack. And if it's water, then at the end you have to deprotonate it in order to get that to work. Why don't you use an acid with a strong nucleophile? I mean, to make it even faster, right? Because it makes a weak nucleophile fast. Why don't you use it with a strong nucleophile?
Because nucleophile will pronate.
and the nucleophile protonates, and then it becomes a weak nucleophile. So, so you kind of screw it up. So if you don't have to add the acid, you don't have to add the acid. That's basically what that says. All right, so water is generally a weak nucleophile. So we're going to show the mechanism for water attacking generic carbonyl group. Let me make a blank slide. And then what I'm going to do is I'm just going to call it, I'm going to do it like this, R, O, and R prime. And the R and R prime could be either H's or C's. They could be alkyl groups or whatever. Okay. And then what I'm going to do is I'm going to talk a little bit about how equilibrium is affected by having different R groups on there. Okay. So for now, right now, I just have the R groups, and we just think of them as anything. All right. And we're going to use water as a nucleophile. What you're going to end up with in the end is this, and the catalyst is H+. Okay. So first step is protonation. And I don't know if you guys remember this. I said this a long time ago, and I think most of you had me for the first semester. If you have acid in the reaction mixture, that's usually the first step is protonation. Okay. You're usually adding it to speed up the first step of the reaction, which is usually the rate determining step. Okay, so what I'm going to do is I'm going to take my H+, I'm going to make it this, because we're doing it in water. And then the lone pair on this oxygen attacks and pulls off one of those hydrogens. So then you end up with that intermediate that we showed before. It looks like this. Okay. And then water could come in as a nucleophile. So water comes in as a nucleophile. It attacks the carbonyl because the carbonyl is more positively charged. And then you're going to end up with this. I didn't put the R, by the way, I didn't put the R prime here and the R here just because they're in there with all the arrows. But now we'll have R prime, and then we have this. Okay. And the positive charge is now on this oxygen, so we deprotonate that. Yeah, and the base in this is water. It's our solvent usually. Like that, and you end up with the product. Okay? And so then the product has R and R prime in it. Okay, so hydronium, H+, or the acid is a catalyst in this reaction because you're using a strong acid to make this hydronium, right? And then during the course of the reaction, this will produce hydronium again. It speeds up the reaction a lot, tens of thousands of times faster with a catalyst. So a little side question here. How does a catalyst, this is a Chem 1B question, but you should know the answer still. All right, just in case you wanted to forget Chem 1B. And you may have learned this in Chem 1A too. How does adding a catalyst affect the equilibrium of a reaction? It doesn't, right? So this is a catalyst. makes it faster. Looks like farter. Excuse me. There, how's that? That really looks horrible. Sorry. Little boy humor. And then doesn't affect equilibrium. Since I can't get all those words in that little space, that's AFFEQ. Doesn't affect equilibrium. Okay, what does affect equilibrium then? Do you guys remember? What determines equilibrium? Concentration does not affect the equilibrium constant, right? It affects the position of the equilibrium, product favored react. Like if you're, like not positioning, it's how much product you can get, but it doesn't affect the equilibrium constant. But what affects the equilibrium constant itself? What's that? Temperature? It can, yeah. Le Chatelier's principle, right? High temperature endothermic reactions push to the right. What other things? Like if I told you, okay, I need you to look up some numbers and calculate the equilibrium constant, what would you do the calculation based off of? pH. No? What's that? Energy? Energy, entropy, right? Free energy is the thing that determines the equilibrium. The energy difference between the reactants and the products determines what the equilibrium constant is. You remember the equation, right? I've used it several times. K is equal to, let's see, E to the minus, or let's see, K, equilibrium is, yeah, E to the minus delta G over something like, I can't remember the exact equation anymore. Let me erase that before I make a fool out of myself. But the idea is, all I wanted you guys to know is the stability of the product and the reactant, the relative energies of product and reactant. So it turns out, right, what determines the difference in energy between these is partially this carbonyl bond. The carbonyl bond is pretty strong, okay? It's a double bond. It's very short. A lot of energy stored in there, in essence, stabilizing energy. But the other thing is the size of these R groups determines the equilibrium constant.
Is the equilibrium, when you talk about equilibrium, also within the area when you talk about the thermodynamic product?
Yeah. Thermodynamic product is the more stable product, right? And because it's the more stable product, over time, if you had 1,000,000 years to do every experiment, or 1,000,000,000 years to do every experiment, you would always end up with a thermodynamic product, right? But we're in a, like, time is equal money regime, and so you don't always get that. You only have a limited amount of time to do a reaction, and in the course of the reaction, you may get the kinetic product as the major product. Okay? So, how does, okay, the size of the R groups affect equilibrium, or the equilibrium constant? These are really good, by the way. You didn't make any for her, huh?
Yeah. Next week.
Man. Wow, a whole week. So how does the size of the R group affect equilibrium? Is it going to be more product favored or less product favored if the R groups are big? Less product favored, right? Because the big R groups, remember this product, right, is tetrahedral, and the reactant is trigonoplanar, so the size of the R groups is not very important here. They're 120 degrees apart. As soon as you add a fourth group to that carbon, now they're 109 or less, depending on the size of the group you're adding, right? And they feel a lot of steric strain. So, I think it's the next slide. Hang on. Yeah, it's this slide. So if you look, so this is acetone, formaldehyde, and then this hexafluoroacetate. Okay. So this is the percentage of each of the reactants and products, right, that you find on these structures when you do this hydration reaction, addition of water to carbonyl function. And you'll notice, if you have formaldehyde and the two R groups are hydrogens, are really small, right? 99% of the product is, or 99% of the reactant, right, is converted to product. And this is the equilibrium, mostly product favored. If you put two methyl groups on there, then all of a sudden it's mostly reactant favored. Okay. And if you put a little bit stronger electron withdrawing groups on it, or a lot stronger electron withdrawing groups on it, then what happens is it becomes much more product favored as well. So that's the electronic effect of having a positive charge and putting the carbons on there, putting the making it more electrophilic in that carbon. If you have like a CH3 on one side and an H on one side, it's mostly reactant favored, right? But not as extreme as both methyl groups and that kind of thing. Okay. Yeah. So you can also base catalyze this reaction. That's one of the fun things about this particular reaction. It's also one of the kind of annoying things about this reaction. In either acid or base, if you don't want the reaction to happen, it's going to happen really fast, right? So, but one of the cool things about it is you can catalyze the formation of that diol, or the addition of the water, right? Either in acidic or basic conditions. Under basic conditions, you don't need to protonate because under basic conditions, hydroxide is a good nucleophile. Right? So when it attacks, again, you get this O minus, which protonates from the solvent. What's this going to make when this part of the reaction happens? OH minus, so it's catalytic. Again, you start with OH in the beginning, you end up with OH at the end, and the reaction goes a lot faster. Does it affect whether or not you have more product or reactant? No, because it's a catalyst, right? Everybody wants to say that, but we often equate faster with more product favored, and it's not true, right? It's just faster. All right, I'm going to have one more, and then I'm going to put these in front of you.
I already have one.
I know somebody who wants one. All right. I'm going to skip over this. We did this one already. All right. So there's this functional group or formation that's called an acetal. And if you take two alcohols and a ketone, acid catalysts, because alcohol is a bad nucleophile, you can get this to form as a product. Now, you think that reaction is product favored or reactant favored? Reactant favored.
Yeah.
Well, the nucleophile is bigger than OH, right? And you still have the two methyl groups around the carbonyl function, acetone, right? And if you remember, when I go back to here, okay, maybe I can't go back to there. There, right? An acetone is 99% reactant, not product favored at all. So this is the overall reaction. This is a very valuable reaction. So how do you make this? This is one that people want to do all the time. How do you make that reaction happen if it's not product favored?
More of that.
Yeah, more carbonyl, more alcohol, or
More acid.
huh?
Acid catalyst.
Acid catalyst makes it go faster, but man, that doesn't affect equilibrium. It would make it go really fast, right? But it doesn't affect the equilibrium. So how do you affect what's one other way to affect the equilibrium? And this is in fact the way we usually do this.
Take away water.
Take away the water. So if you can remove the water, then you can form the product because it can't go back to form the reactant, right? Once you remove the water. So typically, like one strategy for doing something like this when water is a product, a lot of times we'll use toluene as the solvent, and it forms. Do you remember when we did steam distillation last semester, and you boiled? Basically, you boiled. Yeah, you remember because you had it in your backpack. The clove oil out of the clove, right? How come the clove left? Because it got carried out with the water because it made what's called an azeotrope. Well, it turns out toluene makes a really nice azeotrope with water. So you take your reactant and you put it in toluene, you add your acid catalyst, and then you distill it. But what comes out of the distillate is toluene that takes the water from the product away, and so then you can make a high yield product that way. Okay? So basically, you're doing steam distillation, but instead of removing the clove oil, right, you're removing the water. And it's not really steam, it's toluene gas. Just, I don't know. Anyways, that's the same concept, right? Okay. So here's the mechanism. Would you rather me just draw it and you follow along, or do you want me to point at the picture? I'll draw it. Okay, I'm going to draw pictures. Remember, it's acid catalyzed. I have a carbonyl to start with. I'm adding two R groups, two ROHs, two alcohols. Acid catalyzed. And what I'm going to form out of this is this. And it actually happens in essentially two different mechanisms. And I'll draw the first one, and then we'll talk about how the second one works, and then I'll draw that. Okay, so the first one is a lot just like adding water. You got to protonate, right? So I'm going to do the lazy thing. Plus H plus, just to get myself on a clean line. To get to here. I expect that you draw these things out still, but you know what that is, right? And then what happens? Nucleophilic attack. So the first step is to make it so the nucleophile can attack. That's the rate determining step. And so now my nucleophile attacks, which is an alcohol. Goes like that. Oh, that's a CH3 there. And this is O, R, H. Again, if this had been water, that R could have been another H, right? And then I have a positive charge. Oh, there it is. There it's there. Okay. Now, what do I need to do? Looking at the product. Got to deprotonate the H from the OR, and I got to get rid of that OH group, right? Because that's not in the product. So I got to figure out a way to make that go away. So, can do minus H plus, right? Really, that's an alcohol or some base in the solution. And then I end up with this. I still have to get rid of that OH, right? Do you think OH will come off by itself? No, it's a horrible leaving group, right? So it needs to protonate. So this is going to be a plus H plus. And the way that works is that protonated alcohol that you had going to grab one of the hydrogens off, and now it's ready to leave. The question is, how does it leave? Make my life easier and your life easier, I'll call it OH2 plus. Yeah. Well, this OR, right, can push it off like this. And then water leaves, right? And I'm almost to my product. But that's how you get the first one on. You know what I'm going to do? Hang on just a second. I'm going to go one more. This is pretty long, so I'm trying to like space it all out. You get one more guy in there. Okay, that's where I'm at. Now, it doesn't look like the most stable thing, and in fact, it's really not the most stable thing, right? But what am I doing the whole time in this distillation? Remember, we're distilling the water out, right? So there's a water right here. Like at the top up here, what I didn't draw is I'm actually removing two waters. In the course of the reaction. So this is the first water coming off. Which H? Oh, you know what? It's not an H, it's an R group. I want to make it an H, but I'll not do that now. What are you talking about? I'm just going to erase it and pretend it didn't happen. There, like that. Right. Now it's ready for the attack of the second nucleophile. But again, the nucleophile, right, this gets formed because this is being pulled out of the solution the whole time. Being distilled away to drive the equilibrium to the right. And then the second molecule adds, so I'm going to draw R. I don't know where I want to draw it actually. I made this a little bit too tight. This one's going to add like this. And then I'll end up with and then there's just one step left, right? At that point, I just have to get rid of that last proton. Let's see. How do I want to do it? Get rid of that. I should have gone up from there. And then I could have just drawn the arrow back. I could have just done this. Or like this. because oh, sorry, it's not 2 waters. It's 1 water, right? You guys screwed that up. Somehow I got 2 waters out of that. It's just 1 water. Okay. Yeah, so you could drive this product to the completion point just by pulling water out of the system. All right. Good? Sort of? Long mechanism. Just a couple of side notes, and these are reminders. I did mention kind of some of this stuff before, but this is really important in these reactions. Acidic condition. No negative charge in mechanism. So if in the course of the reaction you produce a negative charge on the structure, that means you should have protonated something before you did that, okay? Under basic conditions, you never have like positively charged or protonated positively charged species. But in general, you don't have positive charges in basic conditions, don't have negative charges in acidic conditions. All right. You can actually I guess this is a good point to make. You notice when I did this mechanism, I didn't do this as an SN2 reaction. Like you could have brought this molecule in as an SN2 reaction and just kicked it off immediately. That's because that's what I think what you mentioned, right? The reason you don't do that is because it's a sterically hindered carbon, right? You can't do a backside attack and kick it out. So it's actually closer to a SN1 kind of mechanism where something leaves, but in this case, when it leaves, instead of forming a carbocation, that oxygen donates a pair of electrons to stabilize that charge. Okay. But that is, a carbocation is one of the resonance structures. Okay. So if you do this with formaldehyde, it's easy to do this. It's very product favored. If you do it with anything other than formaldehyde, it's always reactant favored. But we generally get the desired product by distilling the water out. Okay. Now, one of the common uses of this reaction is to form what are known, to form protecting groups on carbonyl functional groups. Okay. So if you have a carbonyl and you don't want to reduce it with sodium borohydride during the course of a reaction, or you don't want it to be reduced, let's say hydrogenation, any of those things, the standard thing to do is to use a diol and make a cyclic acetal out of it. And that acts as a protecting group. Now, in order to do that, you have to distill the water out and you get your product. To undo it, all you have to do is add water and acid catalyst, and the reaction goes back to the reactant. Okay. Let's see what else is there about that. Yeah, you can either do 5 or 6-membered rings when you do this. Turns out 5-membered rings form faster than 6-membered rings. Typically, it's a 5-membered ring. Just trying to think what else I want to cover today. I've talked about a lot of this stuff. So if you go in the forward direction, this is what I was talking about. You remove water. You go in the reverse direction. You add water and acid catalyst. So if let's say you want to do this reaction, right? How do you reduce esters, right? Lithium aluminum hydride is the standard way to reduce the ester. But if you did lithium aluminum hydride directly on this reaction, what do you end up with as the product? If you do if you do this as lithium aluminum hydride, both of these functional groups get converted to alcohols, right? Since one of them is a ketone, right, the strategy is, hang on, is protect this functional group and then do the reduction and then deprotect it. Again, it's like the blocking agent in electrophilic reactions on benzene rings, right? And it's like adding the trimethylsilane to an alcohol, right, to protect that. So you can first do this. And form, and these are fun to draw because it makes it look like your molecule has eyeballs, right? See your little man, right? He's got his hand over here now. Then you can do your LAH. It doesn't react with the cyclic acetal. But it will convert that into, an alcohol. So that would be LAH, and then usually it's like HCl or ROH, not HCl. And then this step here is just H plus and water, like that, okay? So standard strategy is to protect a carbonyl functional group. You can derivatize the carbonyl and then do other reactions like reduction reactions. The only catch is they can't do things that are really acidic, otherwise you deprotect that functional group. So what are the steps involved in this reaction? If you did this, what do you get? See the sequence of reactions, right? I'm going to do this. What is this first step going to do? Protect, right? So this first product, just to show you how these strategies play out. Looks like this. And then what did we do to go to here? Two steps, actually. All right, what? Is that? Well, yeah, there's a step involved where you have to add acid and water. That's how you got rid of the protecting group. But what got rid of this ester like this?
It's oxidation or reduction.
It is reduction. LAH. No, LAH again. Remember, LAH, lithium aluminum hydride, don't forget these things. If you take this and you go LAH, what it will do is it'll convert it into a primary alcohol, right? That's this part. But this comes off as an alcohol as well. So when you protonate it, you end up with two alcohols being produced from the ester. So what they did in this top step, first step was LAH. Second step was ROH. Third step was H plus H2O. You could possibly do the H plus H2O except if you have any leftover lithium aluminum hydride, it'll react violently. So you have to do like a step in between. So you have to protonate the alcohol functional groups. That second step is what adds this on. So this is 1 and 2, and this is 3. Okay. What do they do next? Well, what functional groups changed?
No longer have alcohols.
No longer have alcohols, right? And the carbonyl's missing, right? What is that reminiscent of? Right? Here's, what's that?
We just finished doing
Yeah, it's like a protecting group reaction, right? All they did was add H plus, water, and then they distilled it, they heated it. And you can see it in the structure. That is this. And then get a different color. I'm not sure what I'm doing here. I'm trying to change a color, and I don't really know how I'm doing it. These guys, right? It's those guys. And these are the oxygens that are involved. So it's the formation, intermolecular formation of an acetal. Just distilling the water off, and that's what you get. I actually really want to try this. I think it would be fun. I don't know why. Kind of a boring product to analyze because it has so much symmetry.
is it a solvent?
It's probably a liquid. Yeah. Small, low molecular weight, some polarity, right? So it's not going to be solid, nothing to crystallize it, I think, at that molecular weight. If it was a carboxylic acid or if it was an aldehyde, it might be. All right. Well, that's it for today.